Hello and welcome to a project review of Team 4's final senior design project from spring of 2021, this project being to generate an autonomous piano tutor. To provide some background of this, there are several commercial products in the market which serve similar functionalities, as well as a few advanced systems designed more to interact with the user on an existing piano. Our objective was to kind of combine these two things and create a more compact and advanced Play-O piano system than what exists in most self-tutoring systems, which primarily rely on just playing the song and seeing the notes as opposed to moving the keys. And we wanted to make sure that everything could fit inside of the keyboard itself to make this easy to modify for future groups and be able to check for incorrect input from the user as compared to a predetermined song. The project also has the ability to scan in sheet music, which is one of our major goals here. It'll scan it in via an app, communicate that over to MIDI through Bluetooth, and then play it through the motor drivers. To provide a system overview of this whole project, power is supplied by a ATX power supply. We're using the 5 and 12 volt rails on this. Currently, the power supply supplies power to the motor driver subsystem, the Midi processing subsystem in some ways, as well as the keyboard system, which is where the 12 volt comes in. As a basic breakdown of how all of this is interconnected, the motor driver subsystem sends keystrokes down. The keyboard subsystem, which is just the native systems built into the host keyboard, detect the input through their sensor system and then convert that to MIDI. It goes out the speakers and as well goes into the MIDI processing subsystem. The MIDI processing subsystem is connected to the display system, creating a full loop and allowing user interaction.
The motor driver subsystem includes an Arduino Mega 2560, breadboard wires, 4 Adafruit PCA9685 motor drivers connected in series, and 48 SG90 mini servo motors. The 48 motors are connected via nylon thread to the keys. Those motors are connected to the 4 motor drivers, 1 octave to each driver, which are then connected back to the Arduino Mega. The software performs a setup stage, initializing the motor drivers and setting the motor addresses before entering an infinite loop. During this loop, a MIDI file is read in one event at a time, where it will either turn on the note or turn it off. These functions are performed by setting the PWM input of the associated addressed motor. The system has 3 ranges of dynamics, 4 octaves, and can play at least 7 notes at a time.
The MIDI processing subsystem for this project includes a Raspberry Pi 3B+, a MIDI to USB converter cable, an Arduino Mega 2560, and a USB Type AB cable. A picture of the setup can be seen in the picture on the bottom left. The Arduino and the Raspberry Pi communicate over the USB Type AB cable. The Arduino in this subsystem is the same Arduino used in the motor driver system previously explained. The MIDI to USB converter cable is used to allow for communication between the Raspberry Pi and the built-in MIDI controller on the keyboard. This allowed us to get the keys played on the keyboard to be used for comparison. The Raspberry Pi gets its input from the touchscreen display subsystem, which tells it to either open up Bluetooth, play a song, play a measure, or compare that measure to what the user plays. This next slide will just be a little demonstration of how we use the phone to scan in sheet music, convert it to MIDI file, and then send it to the Raspberry Pi. We start out by using PlayScore 2. We just take a simple picture of the sheet music, which then converts it to a MIDI file. We then just press share as MIDI, Bluetooth, and click the Raspberry Pi 3. As you can see, it says file sent, which is then sent to the Raspberry Pi.
So the display subsystem for our project consists of one Arduino Mega 2560, one Elegoo TFT touchscreen, and 10 breadboard wires. This system offers a variety of screens that would be suitable for a user to control and interact with the project. Some of the screens that are presented include one that allows the user to select one of 3 songs. From there, they could choose to either have the song played on the keyboard or to learn it. There's also a screen that allows the user to indicate that they want to scan in a new song and have it sent to the system via Bluetooth. And the way that this subsystem communicates with the MIDI processing subsystem is through the 10 breadboard wires that are connected across the GPIO pins from the Arduino to the Raspberry Pi. And these pins are what indicates the selections that the user has made, such as which song has been selected or whether the user wants to play or learn the song, and so on.
Something to note here is that this solution came after a long design process. We would like to cover what we have done before in case you, as a next group through or as anyone interested in this project, would like to go back to some of our previous work and start from there. This involved a lot of trial and error. We originally started out, as you can see on the top right, with stepper motors and a piece of fishing line. We continued the fishing line until milestone 1, which was basically just getting 2 octaves of keys working. However, we found that it was very annoying to tie. If you feel that it is better to have the stiffness of the line and you have some way of connecting other than tying knots, it might work pretty well. Furthermore, we eventually switched to nylon thread, which gave us a little bit of slack and a little bit more ability to tie off and adjust. We ended up using taut lines connected between the motors and the keys just to tighten up individual keys. Something else we introduced was tensioners. These are mechanical pencil springs, but any small spring with the right amount of force should do. This allows us to make sure that there is always tension on the line, which aided greatly in tuning. Finally, we did drill eyelets into the system. As you can see, they are the silver blocks in the bottom left picture attached to the blocks of wood that the keys are currently laying in front of. However, they weren't entirely necessary, but they did help add some stability. If you have a different case design, since this is portable, we would suggest experimenting yourselves.
The way that each keys were actually played was through a system of string that is routed beneath each of the keys and then through the casing of the keyboard. Each string is tied to both the underside of each of the 48 keys and then again to its respective motor. And here is a demonstration again for release with the lid on, also seeing interaction with the user interface on the right. Right, and in this demonstration, you can see 3 notes being played automatically by the keyboard, which is then repeated correctly by our user. And if you can see on the right side of the casing, a green light indicating that it was played correctly. And then 3 more notes played by the keyboard, which is then our user plays them incorrectly, and a red light indicating that the user had played the notes wrong.
The performance characteristics of our system include about a 25 watt maximum power draw as measured by a kilowatt power meter. The amount of keys that can be pressed at one time has been tested for up to 7 notes at once for the automated playing of notes feature. We ran our system for 36 hours at a rate of about 1,000 keystrokes per key per hour, resulting in 2 failures and approximately 35,000 actuations per key. Neither of the failures were determined to be as a result other than of an improperly tied knot, and all moving parts are user replaceable, assuming you have the correct tools. For our post-mortem, we noted that our strengths include the fact that our final system reliably pressed down keys with a 99% hit rate and played the correct notes from MIDI files. Everything except the ATX power supply was able to fit inside the keyboard's case, and the total cost of the individual components actually used to make the final system was within budget. Potential improvements include designing a custom case to allow all components to fit inside with ample breathing room and reduce obstructions for the threads to get caught in. It would also allow for less adjustments on the knots that were tied. Also, we could use a different type of motor to allow for more dynamic levels than the servo motors we used seem to be capable of. Dynamic levels are simply different volumes of sounds and were determined by the speed of our motors. We could also refine our user interface a bit by adding some more modes of operations and designing a better system for verification of keystrokes to determine if a keystroke is correct or not. We could add in an LED for each key when it is depressed or it's supposed to be by the user, as is standard in many commercially available systems today.